This doctoral dissertation is a result of an international collaboration between Gdańsk University of Technology and Supergrid Institute. Gdańsk University of Technology was established in 1904. It is present in the Shanghai ranking, and it is the second best research university in Poland. Supergrid Institute is a research and innovation center developing key technologies for future electricity grids and renewables integration. In the 21st century, we are becoming aware of the environmental issues of our planet. The renewable energy sources and electric vehicles are being developed to face those issues. In power systems, we observe the rise of direct current. HVDC, high voltage direct current, is now reserved to point-to-point transmission of bulk power over long distances. We can notice a large number of existing and planned HVDC links in Europe. MVDC, medium voltage direct current, is an emerging technology which may give birth to DC grids. One of the enabling technologies of DC grids is the isolated DC-DC converter. An interesting isolated DC-DC converter topology for bidirectional power flow applications is the dual active bridge. The dual active bridge is composed of a voltage source inverter, transformer, and a rectifier. The transformer, the medium frequency transformer, is the key component of the dual active bridge. The dual active bridge exists in several topology variants. The three-phase dual active bridge offers some benefits compared to the single-phase variant. It is more compact, it is more energy efficient, and it is more optimized. However, no three-phase transformer at high power and medium frequency has been reported. The requirements of the medium frequency transformer in the dual active bridge converter are different from the requirements of the grid-connected transformers. In particular, we have a free choice of the operating frequency, because we are not constrained by the 50 Hz grid requirements. The Faraday law of induction shows that increasing the frequency results in a smaller transformer. This is observed in the domestic power supplies. We also know that the transformer cost is roughly proportional to its weight. So the medium frequency transformer is likely to be smaller, lighter, and cheaper. However, there are still many technical challenges to address in high power applications. Let's say in the range of hundreds of kilovolt ampere. This brings me to the subject of this doctoral dissertation and to the formulation of the thesis. Thesis 1 is related to the precision of the feedback Preisach model of hysteresis in medium frequency transformers. Thesis 2 is related to the approximation of the equivalent magnetic permeability with an exponential function of the number of parasitic air gaps. Thesis 3 is related to the influence of the nonlinear mutual inductances on the accuracy of the three-phase transformer equivalent circuit model. Now, I will detail the first selected subject, modeling of medium frequency transformer. I propose an equivalent circuit model of the dual active bridge converter with the three-phase medium frequency transformer. The inverter and the rectifier are modeled with the controlled voltage sources. The transformer model includes the primary and secondary winding and an equivalent circuit for core power loss. I selected the Lagrange energy method to derive a physically motivated model. The Euler-Lagrange equation, the capacitive elements are neglected because I demonstrated that in the considered analysis they have a negligible effect. The matrix of inductances, MS, is split into two matrices. the matrix of nonlinear magnetizing inductances, and the matrix of linear leakage inductances. In the matrix of the nonlinear magnetizing inductances, I define a magnetizing flux, Φm, which is a function of two variables, two magnetomotive forces, theta g1 and theta g2. In order to calculate the equivalent circuit model parameters, I developed a finite element model of the medium frequency transformer. The material properties were considered homogenized. Neumann boundaries were applied to the background region, meaning that the normal of the magnetic field strength was equal to 0 at the limits of the region. I performed a series of magnetostatic simulations with different magnetomotive force excitations. These simulations provided me with discrete values of the magnetizing flux in the function of two magnetomotive forces, theta g1 and theta g2. The values of the magnetizing flux in the left column of the transformer are displayed in this three-dimensional plot. Furthermore, I proposed a surface interpolation to obtain an analytical function of the magnetizing flux. This allowed me to calculate the partial derivatives required in the equivalent circuit model. In this figure, we can observe the effect of the magnetic cross-saturation in the three-phase core-type transformer. I developed a three-phase 20 kHz transformer prototype for 100 kW, 1.2 kV DC-DC converter based on silicon carbide transistors. We see the transformer prototype, inverter, and rectifier. I performed a number of experimental investigations and a number of simulations with the developed model, both in transient and steady state. I observed a very good fit between simulation and the experimental results. I present here an example result of transformer no-load inrush test, where the medium frequency transformer was supplied from the inverter. Three colors correspond to the three phases of the transformer. The dashed line is the simulation result, and the solid line is the measurement result. A very good fit is observed between the simulation and the measurement. I presented this result in IEEE transactions on power delivery. This result proves thesis 3. Now I'll move to the second subject, modeling of magnetic hysteresis. I reviewed the macroscopic models of magnetic hysteresis, and I selected the Preisach model for further analysis. I developed a feedback Preisach model according to this block diagram. The upper block presents the classical Preisach model with the double integral of the Preisach distribution function, and the lower block presents the feedback function. I propose the feedback function to be a third-degree polynomial. I propose to approximate the Preisach distribution function with a two-dimensional Gauss functional series. In the equation, we see the parameters a, sx, and sy that have to be defined. And in this three-dimensional plot, an example Preisach distribution function is displayed. I proposed an experimental approach to define the Preisach distribution function parameters and the feedback function coefficients. I developed a test bench where the three-phase medium frequency transformer is supplied in a special manner from a single-phase power supply. In this test bench, we see the medium frequency transformer, AC power supply, oscilloscope, voltage, and current probes. The excitation current and the electromotive force were measured. The electromotive force was measured in an auxiliary coil to reduce the contribution of the leakage flux. The magnetic field strength and the magnetic field density were calculated under some simplifying assumptions. The Preisach distribution function parameters and the feedback function coefficients were fitted to the measured quantities using an optimization algorithm. I simulated the feedback Preisach model, and I present here the major hysteresis loop. The solid line is the simulation result, and the dotted line is the measurement result. With the same model and the same model parameters, I simulated a minor hysteresis loop. The minor hysteresis loop corresponds to the nominal operating point of the prototype medium frequency transformer. The solid line, again, and the solid line is the simulation result, and the dotted line is the measurement result. And the dashed line is the major hysteresis loop. We see that the simulation fits well the measurement. I submitted this result for publication in IEEE Transactions on Power Delivery. And this result proves the thesis 1. Now I'll present the third subject, analysis of parasitic air gaps in the ferrite core of high-power transformers. In high-power medium-frequency transformers, the ferrite core has to be assembled with multiple I cores. This is because for such big transformers, the C cores and the E cores do not exist. As a consequence, in the core assembly, there are multiple parasitic air gaps. In this figure, I present the core assembly of the prototype medium-frequency transformer. We see the multiple I cores and the multiple parasitic air gaps. I present 2 example assemblies of 4 randomly selected I cores. We see that in these 2 assemblies, the air gaps have different sizes. This is due to the dimensional tolerances of the individual I cores. My conclusion is that in such a core assembly, the parasitic air gap size is unpredictable. As a consequence, it is not possible to predict the average air gap length, the effective magnetic permeability, or the magnetizing inductance. And this may be a problem in the design of isolated DC-DC converters. I analyzed the average air gap length of 4 medium-frequency transformer prototypes. The average air gap length of 4 transformers is displayed in the function of the number of parasitic air gaps. The stars corresponds to the prototypes with 4 air gaps, 6, 10, and 14 air gaps. Contrary to what would we expect, the average air gap length is a nonlinear function of number of air gaps. This is the result of the cumulating I-core misalignments. I propose the scaling function allowing to estimate the equivalent magnetic permeability in ferrite core transformers. The function is defined as a ratio between the equivalent magnetic permeability and the ferrite material permeability. I found out that the ratio can be approximated with an exponential scaling function of the number of air gaps. This exponential scaling function is presented as the red line, and the stars correspond to the measurements on prototypes, and we see that the approximation is good. I presented this result in the Energies journal, and this result proves the thesis number 2. Now I present the last subject, thermal design and measurement of medium frequency transformer. When designing the three-phase medium frequency transformer, I developed a computational fluid dynamics model. I consider a simplified geometry with windings, core, and fans. I assigned a constant power source to the windings and the core. The fans had a constant pressure airflow characteristics. The bottom face of the background was defined as a wall with 0 heat flux. Other faces were defined as openings at 40 degrees Celsius. This model allowed me to adjust the design of the prototype medium frequency transformer. Once the prototype was ready, I performed a thermal test. It took approximately 6 hours to reach the stabilized temperature. In this test, the medium frequency transformer was within the dual active bridge converter at the nominal operating point at 100 kilowatt. I measured the temperature thanks to the thermocouples placed around the transformer. The hotspot was identified in the core in the central column. I compared the simulation and experimental results. The temperature distribution on the core surface is the result of simulation. The text in red shows some simulated values, and the text in black shows the measured temperature values in the same locations. We can observe quite a good fit. Now, I would like to conclude this presentation with the main achievements of my dissertation. I developed and validated experimentally several mathematical models. I demonstrated that the Lagrangian model of the three-phase medium frequency transformer, taking into account the effect of magnetic cross-saturation, is accurate in steady state and transient analysis of the dual active bridge. I proposed a finite element model of the transformer, allowing to calculate rapidly the equivalent circuit model parameters. I developed the feedback Preisach model of hysteresis in the medium frequency transformer. I developed two three-phase medium frequency transformer prototypes for 100 kilowatt DC-DC converter. These are first worldwide three-phase transformers in this power and frequency range. The power density is 4 kilovolt ampere per kilogram. This is roughly 10 times higher than an equivalent 50 Hz transformer. I measured the DC-DC converter efficiency at 99.2%, what is a very high efficiency value. I performed several analyses. I proposed an analysis of parasitic air gaps in high-power ferrite core transformers. I demonstrated that the average air gap length is a non-linear function of the number of air gaps. I proposed an exponential scaling function of the equivalent magnetic permeability. I validated experimentally the thermal design of the prototype medium frequency transformer. The results of my dissertation were published in several journal and conference articles. One journal article published in IEEE Transactions on Power Delivery. One journal article published in MDPI Energies. And one journal article submitted for publication in IEEE Transactions on Power Delivery. I published 2 conference papers, and I co-authored 6 conference papers directly linked with this study. I identified several perspectives for future research and development. The feedback Preisach model of hysteresis could be implemented in the three-phase medium frequency transformer equivalent circuit model. And it could be extended, taking into account the effect of temperature. The equivalent magnetic permeability scaling function should be validated with a large number of transformer prototypes and elementary core dimensions. A precise comparison between the single-phase and three-phase medium frequency transformer and DC-DC converter should be done. The power loss measurement technique for medium frequency transformers should be studied. I think that the reliability of power electronics converters should be addressed. In my opinion, the electromagnetic interference is still the main challenge in silicon carbide-based power converters. Thank you for your attention, and I would like to finish this presentation with the motto of Gdańsk University of Technology. History is wisdom, future is challenge. Historia mądrością, przyszłość wyzwaniem. Thank you.